Good morning, Mr. Patty here. I wanted to take a couple minutes to record a video about Desmos and analyzing the harmonic motion of the pendulum and the harmonic motion of the bouncy spring, as well as analyzing with the Desmos. As you probably know now, if you watch the videos, there's a square root relationship or an inverse square root relationship, and I want to see how you could get the proper equations for those using Desmos. So let's get started. So first thing I'm going to do is bring up the Phet simulation. Do a quick search for springs. Looking for the Spring and Mass Lab. Start this bad boy up. And we have the situation here. I'm going to put a 50-gram mass on here, leave the spring constant where it is, and if I get this started, we can see it slows to a stop here. That's because they have the damping on. I'll turn the damping off. Get this going. We can see the energy over here, which I think is cool, but what I'm interested in is how does the mass affect the period. So, one of the ways in which we're going to analyze this is we're going to time it for one full bounce. Now, when I go to time it for one full bounce here, I got to be really quick with the counter. So 3, 2, 1, go. Stop. So about 0.7 seconds. Now, that's not the best way to do this. What I should do is count it for 10. Let's see if we can do that. Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we got about 6.23 seconds for 10 bounces, which means that for one bounce, we got 0.623 seconds. So it's a little problematic if you're trying to do it with just one, but let's see how to analyze this. So now I go to Desmos. If I'm going to analyze, I'm going to need a table. So my X is the mass. I started with 50 grams, and I got 0.623 for the period. Okay, let's do another one. So let's increase this to 100 grams. Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so 8.92 for 10, so 0.892 for 100 grams. Okay. So let's go up to 150 now. Now 150, it's going pretty slow. I can probably figure it out here. Ready, set, go. Stop. So 1.13, let's try again. 1.12, that seems pretty good for 150 grams. Let's go 200. Ready, set, go. So 1.2. 1.32. Oh, those are far apart. Let's try again. Ready, set, go. 1.27. Let's do 250. Ready, set, go. 1.32, let's try again. 1.42. 1.35. All right, so now when we analyze our graph, we're going to have to use a little wrench here because our x data goes from 50 to 250. So I'm going to make my x 0, 250, and I can see my data. My y values go from 0 really only up to like 1.5. So now I can see my data really nice. This is not linear. If it were linear, a doubling here would give me a doubling here, or a doubling from 100 to 200 would give me a doubling, but it doesn't. So we can see this is somehow a shape like this. So let's get a square root and see if that works. Add an expression, y1, squiggle. We need some coefficient. We'll use a. You could use any letter here. x1. And then we're going to use the shift 6 to get the caret. And if it's a square root graph, it's a 0.5 power. And you can see that this fits my data very nicely. This one's on, this one's on, this is a little above, this one's a little bit below, and it looks really good. And so our A value is about 0.088. And so that's the square root function. If we wanted to change the situation, okay, let's stop it and let's go back here. Settle down. Each of these little ticks on the spring constant here, this is a 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So you could actually use this slider here to get the spring constants, and that's what we're going to do. So let's start down here. I will choose 100 grams again. Okay. Spring constant is 3, mass is 100. Let's see if we can't measure the period here. And go. Stop. So 1.13, that's close. Let's try again. 1.2. 1.12. So new data. So spring constant is 3 and 1.12. So let's make the spring constant, so 3, 4, 5, 6. So the spring constant is 6 now. So it's a little fast now, so let's do 10. Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So about 8.15, so spring constant 6, 0.815. Go to 9. Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so 0.658. All right, let's go to 12. Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0.57. So let's get rid of this one here. So I have my new data here, and I'm going to need a new expression to analyze it. All right, let's fix the x-axis here. I only need to go out to 12 here, so let me get the wrench out. I can see my data. Looks pretty good. So it's going like this. That's an inverse variation. So when I do the equation, y2, squiggle, I have to use y2 because my data is x2, y2, coefficient. And if it's inverse, we are now divided by x2, and I'm going to do shift 6 for the caret, 0.5. So to get an inverse expression, you got to put your independent variable in the bottom. And we can see we have a, not straight inverse, but inverse square root, because we use the 0 power again. And so that's how to use the Phet Simulation and the Desmos to see if we can't get those variations. So hopefully that clears up what's going on with those labs. Try to get those labs done, watch the wrap-up video, and then once you're done with the wrap-up video, do the progress check. And if you're done with the progress check, then you can move on to the homework, and then we'll have an assessment after that. Good luck, and let me know if you guys have any questions.